Alan Turing is an excellent segue for our next speaker, considering that Julian just walked us through the pleasures and effects of repeated death on the human brain and the possibility of, if you believe in the singularity, the possibility of immortality and life without a body. It's now only fitting that we now approach this from sort of the opposite perspective about creating virtual life, of creating artificial life, so to speak. Alan Turing, of course, was the original sort of father of artificial intelligence, which is one of the great sort of areas of interest to the Beckman Institute. Our next speaker is Dr. Stephen Levinson, who's a full-time faculty here in artificial intelligence. I could walk through a very long list of his achievements that I have here. He's a member of the Association for Computing Machinery, a fellow of the Institute of Electrical and Electronic Engineers, fellow of the Acoustic Society of America, founding editor of the journal Computer Speech and Language, which sort of leads to what he'll be talking about today, which is basically, can we teach a robot to learn? Can you teach it the way you would teach a human being? Can you create a form of artificial life that begins to resemble the life as we know it? This is something that they once thought in artificial intelligence research would be easy, that we would have it by now, and then it became astoundingly difficult, and I'm very curious to hear exactly where we are sort of in the scope of it in terms of, how easy, how difficult, and how soon. Dr. Levinson.
Okay. Is this microphone on? Yes. Okay, good. So, good morning to all of you on this lovely April Fool's Day. It's a pleasure to be here. You can see the title of my talk, and it's got the wonderful world in there, robots. We're all fascinated by robots. And we all know the canonical story of robots. Robots are built, they get very, very smart, they achieve consciousness, they decide that the human species is inappropriate, and they decide to take over, and a great battle ensues, and then the human spirit triumphs, and the robots are put in their place. And that's a nice narrative. It has absolutely nothing to do with reality. And what I want to do today is tell you a little bit about what the reality is, and with some speculation, what it might someday be. This reminds me of an interview that I had recently. As I'll show you at the end of the talk, we have a very elaborate, fully anthropomorphic robot in the lab, and you'll get to see it in operation. But when we acquired this robot, lots of people were interested in it purely because it was such an elaborate robot. But one of the interviewers said to me, boy, you're not going to build a Terminator, are you? And I said, there is no science or technology to support the construction of a Terminator, but if I could build one, I would do it in a heartbeat. And that is an absolutely true, however terrible you may think, it's an absolutely true statement. So I want to try to juxtapose two ideas in this talk. One is that there is inherently no reason why we can't build a Terminator. On the other hand, at the present moment, the science and technology are vastly inadequate to do anything even remotely like what you see on the Hollywood screen. And what I'm going to do is mostly talk about the theory, why that's true, what we know, what we don't know. And this is going to be sort of a little tiny eat your spinach talk. At the very end, if there's time, I'll show you some home movies about what is or is not possible. The thing to remember is that these robots are simply an experimental platform on which to do the science trying to understand mind, brain, and language. The fact that we use the robots is only important in one specific way, and I'll get to that, but it was alluded to but by the sheerest, dumbest luck, it was alluded to in the previous talk, and Julian seems to think that, that the mind can exist as bits in a computer. This is absolute horse feathers, and you need the robot. You need an embodiment in order to have a mind, and I'll try to explain why that's so. But first, a little background. As was mentioned earlier, there is a thing called the strong theory of AI, which traces back to Alan Turing. And this is an absolutely fascinating story. I wish I had time today to talk to you about it. But Turing did, in fact, invent the computer, but that was not his purpose. What Turing was trying to do was to answer questions about the nature of mathematical truth. And he came from a long line of people who were working on that, descended from Hilbert, the great mathematician David Hilbert, in 1901. Anyway, in 1936, he proves his famous undecidability theorem, and what came out of this was the notion of universality, which Julian mentioned. What he didn't mention is, at least not directly, is that the internal representation in the computer is symbolic, and this leads to the Church-Turing hypothesis, which says that if you can describe how to do something, then a universal machine can do it. So this was the basis for Turing's thought, and over the years, by the way, I have to say that Alan Turing was a once-a-century genius, and as such, he got himself into a lot of trouble. And he spent a lot of time working on all sorts of important projects, but he never got to build his dream of the computer until very near the end of his life. He had it all worked out on paper, but he never got to build it until nearly the end of his life. He did come to the United States in 1945, and he witnessed the construction of the American computer, ENIAC, but he didn't get to build his own until later. What happened was that he had all these wonderful insights, and his friends knew that he understood important things, and they convinced him finally to write some of them down. And most of these ideas appear in a 1950 paper which was published in the psychological journal Mind. And we all know that in this paper he proposes the universal Turing machine as a model for mind. And we also know that this is the paper in which he describes the Turing test, which he called the imitation game. What most people do not know about this 1950 paper is this little quote. This comes from the next to the last paragraph in that paper, in which he says, essentially, you can read it for yourself, but what Turing is basically saying is that the mind is embodied, and that without a sensory motor periphery, you don't get mind. And unfortunately, at the time, the proposal that he makes in this little paragraph was technically infeasible, and Turing perhaps did not understand the importance of motor function. He certainly understood the necessity for the sensory periphery, but very likely not motor function. It's interesting that as a result of Turing's ideas, people immediately felt that artificial intelligence was right around the corner. It seemed that Turing's theory was the Newtonian mechanics of psychology, and things would happen very quickly. Well, as you know, for a variety of reasons, they didn't. And as I look around, and I know many of you are not part of the Beckman Institute, so I'd like to show you this. The Beckman Institute was essentially founded in order to fill in the gaps, to explain why Turing's ideas had not so easily come to fruition. And the idea was that you need the social and life sciences on one hand and the engineering and physical sciences on the other hand, and together they build their way up to the ultimate goal, which is intelligence. Now, one of the reasons why my study is so appropriate for the Beckman Institute is that we engineers listen to those people who study biology, behavior, cognition, cell biology, all of that stuff, and we try to glean from that what it is that we can implement in mathematically reasonable, computationally tractable models. And so it's our job to integrate all this and ultimately get to the ultimate goal of intelligence. Now, unfortunately, the prospects for this are not good. And I just want to take a couple of minutes to talk about this. There are presently intractable problems in implementing the pyramid that I just showed you. We have a bunch of things that we would like to do. We're very worried as a society about security and defense. We're very worried about health. This multimodal data management is my way of avoiding saying the internet, which device I hate and the use of which I despise. But in any event, that has come to define modern life. And we don't really know how to use any of these things and integrate them appropriately into society. This is going to require fundamental research. And fundamental research is very difficult to do because, first of all, it's expensive as hell. Second of all, it doesn't necessarily go anywhere. People think of research as a fire hose. If you have a problem, you take your fire hose and you train it on the problem and you put out the fire. That's not what it's like. Research is like a shower. It rains everywhere, and you don't know where things are going to result from it. I guess the biggest problem is that the unification of all of the sciences that are necessary to build a true artificial intelligence are grounded in mathematics. Now, we presently do not have all of the mathematics that we need. Much of it is to be invented. But until everyone has the common language of mathematics, it's going to be very difficult to integrate all of these many ideas. Here's the basic premises of our project. Most psychologists believe that we have a mental representation of reality. It ultimately gets overlaid with a linguistic structure so that we hear our thoughts as our mind's voice. Cognition is embodied. The brain in a vat, science fiction stuff, is pure nonsense. Cognition is integrated. It requires a complete sensory motor periphery. Cognition, as it appears in the human, is not due directly to computation in the sense of Turing. Rather, it's due to associative memory, which is a much less powerful computational model. The contents of the memory are learned by reinforcement from experience in the real world. And then language is driven by meaningful, purposeful behavior. That's what humans are about. We have no, there's no value if we're not driven by this meaningful, purposeful behavior. Let me just tell you a little bit about what associative memory is. This is a cartoon. You can imagine this in abstraction. In our minds, we have things which I, for want of a better word, call concepts. Take the concept of an apple. It consists of many different things. The smell of an apple pie, the taste of biting an apple, the visual percept of an apple, the crunch that you hear when you bite into an apple, the physical weight, the mass of an apple, and other experiences that we know about apples. We know about Johnny Appleseed and other things like that. Now, the interesting thing about associative memory is that it is a computational function such that if any one of these nodes is stimulated, all the others get stimulated. So when you think of one thing, all the other thoughts flood to you. And this is what the brain is doing. This is the only thing the brain is doing. It's just simply making associations. But it's this vast network that's able to make such huge associations that we can actually function in the world. And of course, this machine can be modeled, implemented on a Turing machine, which is, as was said before, universal. So how do we get meaningful, purposeful behavior? We start with sensory motor signals. We somehow mysteriously convert those to symbolic representations. We have notions that are built in of correlation and utility. That is, if several of our sensory motor channels all tell us the same thing, that's a high degree of correlation. That becomes what we call a salient measurement, and we remember it. And then that has a utility. It allows us to do other things. Also built in is spatial reasoning. Actually, I shouldn't say built in. It's acquired by being able to move our arms and limbs and eyes and so forth. This gives us a sense of spatial reasoning. This, in turn, allows us to develop a notion of causality. Humans have a hardwired notion of causality, and that is things that happen closely together in space and time are causally related. That's the way we actually think. That, of course, is completely fallacious, but it is in fact the way we think. And we do analogical reasoning. There is no facility in the human brain to do formal logic. We reason analogically. A is like B, therefore whatever A does, B does. This is what comes naturally to us. So we thought maybe we could try to emulate all of this. And I'm going to skip a bunch of stuff here because there isn't time to do it. But I would like to tell you a little bit about what we build into the robot. So we build in some hardwired behavior. First of all, the robot is irritable. If you do something to the robot, it's going to do something back to you. It has certain audio-video preferences. It likes sounds that have a certain frequency range. It likes bright-colored objects. It likes clearly demarked contours. It doesn't like threats, so it regards shadows as threats. It regards big objects moving toward it as threats. It gets hungry. When its batteries get low, it gets hungry and it tries to get fed. It has a tactile sense, which it uses to detect boundaries in the physical world. It has a sleep instinct. So when its memory gets overloaded, it goes to sleep and tries to restructure the memory. And it has a built-in reward system. And as a matter of fact, in today's day and age, you hear a lot about reward systems because we're very worried about drug addiction and the dopamine system in the human, which is responsible for our internal rewards. The robot also has to adapt to the outside world. It does that by autonomous exploration. It has an instinct to imitate. Some neurophysiologists think that there are parts of the brain called mirror neurons that enable you to do that. I don't know whether that's true or not, but certainly we think imitation is important. We also allow for direct instruction of the robot. That is, we can take its limbs and move them, and the robot can perceive what we're learning. And ultimately, the symbolic representation of the external world gets represented in our own natural language, which is learned by experience in the world. Now, how am I doing on time? Okay, good. So let me tell you a little bit about what we've been able to achieve. This is an early robot that we built. This robot learned to run a maze. It wasn't programmed. It wasn't a wall-hugging device. It wasn't one of these idiotic mouse in a maze things. This robot learned by experience to run a maze. And what it learned in particular was that if you pick it up and take it someplace else, and then a little bit later put it down somewhere in the middle of the maze, it'll look around and it'll figure out exactly where it is, and it'll go to the exit. And this is done on the basis of visual navigation and object recognition. Now, We also did some interesting things with voice command. We wanted the robot to learn some spatial reasoning. So we just talked to it the way a parent talks to a child. And the idea, this is where irritability comes into play. The robot is irritable, so when we talk to it, it does something. And usually it does the wrong thing. So we push it around and to get it to do the right thing. And ultimately, it learns a whole bunch of spatial reasoning and spatial commands. I'm not going to play this video for you. Sort of the culmination of what we were able to do with these little trash can robots is we were able to integrate spatial navigation, visual perception, audition for speech and language, and some interesting behavior. And let me see if I can if I can play this video for you. I think this will be self-explanatory. I just want to say one thing before playing the video, and that is that what you're seeing here is entirely, and I repeat, entirely learned behavior. The robot is not programmed to do what it's doing. It has learned this by experience, by interacting with us in the laboratory.
Illy, over here. Illy. Cat.
He said cat. You may not have heard that. So the robot's thinking, what does he mean? Cat. And eventually he'll figure something out. This is in real time, so you'll have to bear with me. So at this point, he's more or less found the cat. And now the question is how to get there. And this is all learned. I mean, you take this for granted. But if you see something, you know how to go to it. The robot has learned the same thing. And there's going to be an accident that happens in a couple of seconds. And the robot makes a mistake and gets loused up. You may be able to notice him looking around. You notice the eyes drop. He's lost sight of the cat. So we can see what's going on inside his mind, so we remind the robot, go find the cat. And this little end zone dance is actually part of the learning process. The robot is pushing the cat around and taking note of what happens when it does so. This was really very exciting. We did one more experiment with this robot. I don't have the video here. This is just a still image of it. But in this case, the robot learned enormously sophisticated things. Namely, it learned a much more elaborate language in which there was some grammar. It learned a bunch of production rules of the grammar, and moreover, it learned how to talk, so that the robot can move an object around, and then it can tell you what it's actually done. And it does that using its acquired grammar. And so finally, that brings us to where we are now. Based on our success with these little trash can robots, we decided to go to a fully anthropomorphic robot. And the idea here is that with an extremely rich sensory motor periphery, we have much more information available to us, and therefore the robot can learn many more interesting things. You may think, well, that's just making the problem harder, but the truth of the matter is that the world is very highly structured, and if it weren't so structured, we wouldn't be able to navigate within it. So the fact that you have a much richer sensory motor ability to measure the outside world, that makes possible more elaborate behavior. And this robot is actually in the lab. You might be interested in knowing that this robot is called the iCub. It's built by a European consortium of about 30 industries and companies. You can find the iCub on the web. We were able to get one through a competitive grant procedure, and we were successful. We have the only one in the Western Hemisphere. And I think the iCub consortium was particularly interested in our notions of language acquisition, and that's why we were awarded this wonderful, elaborate robot. I'm just going to show you some of the things that it's physically capable of. This is sort of interesting. And this robot is actually in our lab. We've taken the skin off so that you can see the hardware a little bit. One of the interesting things about this robot is that the design began with the hand, and it's a fully articulated hand. Actually, all the joints and motions are very human-like, but the hand, especially with the prehensile thumb, was very important in the design. So we're just beginning with this robot, and we hope that we can get some truly elaborate behavior, and with a little bit of luck, we'll be able to build a Terminator, and then we will determine everybody's life and death. Okay, so thank you very much.